All right. Okay, well, thank you. So, yeah, as announced, I'm going to talk about tau neutrino studies. I changed the title. And I'm doing this with KM3NeT ORCA. So first of all, what is ORCA? Now, well, ORCA is one of the two KM3NeT detectors in the Mediterranean Sea. ORCA is in front of France, kind of. And eventually, we plan to have 115 cable strings that we call detection units, or short DUs. Each of them has 18 photosensors that we call digital optical modules, or short DOMs. Right now, since May this year, we have exactly 28 of those DUs placed already. Yeah, the green ones and the purple ones over here. And since we deploy them all in stages, we made some nice infrastructure underwater so that we can operate each of the DUs separately. And so we can take data even though we haven't reached our full 7 megatons of instrumented mass yet. So in that sense, I will talk only about the first 510 days of data that we have taken with ORCA 6. So those 6 purple DUs up here. Now, when we're talking about data in KM3NeT, we have 2 event topologies similar to IceCube. The first one is a track. In that case, we have a charged particle that enters the detector, and it doesn't really interact. So it just moves through, emitting some Cherenkov light along a line, the line through which the particle enters. So you can see here in blue the early times, and in pink the late triggers, and the size of each DOM here shows the deposited energy. And now the other topology we have is called a shower. It's here on this side. Eventually, it's just a charged particle entering. It interacts immediately and starts a cascade of secondary particles that then all emit some radiation. So eventually, we see it as more of a spherical shape. Now, to distinguish between those two and between background and signal, we use boosted decision trees usually. So what we do is we simulate a Monte Carlo data set. That's what you can see here in this plot, or in these plots as colored stuff. And then we compare to data, which is the black points, just to check that our Monte Carlo data set makes sense. So here in the residual plot, you can see that our data Monte Carlo agreement is pretty good. And then with our boosted decision trees, like starting with background, we try to get rid of, we try to make cuts in our decision tree scores and, yeah, decide on stuff. So backgrounds that we have here are K40 isotopes that are radioactive and would produce some radiation. Then we have bioluminescence and we have atmospheric muons. The first 2 of those backgrounds can be rejected pretty easily without using BDTs. For the atmospheric muons here in green, we just take the score and like we reject this part where there's a lot of green stuff. And then we define 2 samples, a low purity sample, which still has some atmospheric muon contamination, but it's not that bad. And the high purity sample, which has barely anything at all. And then for tracks versus showers, we again train another BDT. And you can see here the tracks and the showers. Well, and doing this will give us a table like this. So here you can see the different event types that we simulated in our Monte Carlo sample with these corresponding numbers. And then you can see the total Monte Carlo set and the total data for each of those BDT classes. And there are a few really interesting things. The first one being here in red, is that we can reject atmospheric muons pretty well. So we have 118 atmospheric muons out of 5,800-ish total events. So that's pretty good. Now, the other interesting thing concerns the tau, or the charge current tau neutrinos. Here we have 185 tau neutrinos, which doesn't seem that much at first. But then if you look at the 14-year sample by Supakami Okanda, we got exactly the same number. Just nice way to brag. Well, especially because we took almost 2 years for that, not 14. Anyways, then in the tau neutrino sample as well, we can see that it's mostly showers. That's pretty natural. But even among the total Monte Carlo sets, the showers are still, or the tau neutrinos are still pretty subdominant. So we can't really differentiate event by event to get our tau neutrinos, but we have to do this with statistical means. Now, this being done, we can try to figure out what to do with the taus, because there's got to be something interesting here. And well, the first thing that pops into everyone's mind is the cross-section. Now, the interesting thing is that if we want to measure a tau neutrino via charge currents in our detector, we need it to be highly energetic or energetic enough to produce a tau. And using simple kinematic arguments, we can guess that we need at least 3. And so that does something to the cross-section. Like if we look at this plot where you can see energy versus this factor K, it's pretty much proportional to the muon neutrino cross-section versus tau neutrino cross-section. You can see that it has a very steep cutoff here at the 3.5 GeV. And such cutoffs are pretty sensitive to beyond the standard model physics. So if there's something weird going on, then we should be able to see it here, which means studying this makes a lot of sense. Also, current cross-section measurements for the tau neutrino have pretty gigantic errors. So always great to add to that. And so we're measuring cross-sections. To do so, we do a pretty simple approach. So we say that the measured cross-section has a shape given by some theoretical estimate. In this case, it's done via Gini code. And then we produce a normalization that really just pushes it up and down. And we fit this by using a maximum likelihood fit, where the three parameters are the mass difference between 3, 1 and the oscillation angle, the 2, 3, and then, of course, a parameter of interest and systematics, because that's what we're sensitive to in KM3NeT. And doing the fit will give us something like in this plot. So what you can see is the cross-section versus the tau neutrino energy. The dashed line shows the Gini cross-section, and then as a cross, you can see our measurement. The energy of the measurement, it's 20.3 GeV. It's the median energy of the Monte Carlo data set. So you can see the distributions of our Monte Carlo data sets over here. And well, so we got some cross-section. So let's compare to the others. For this, we're using the normalization again, because that's energy independent. And well, as comparison, we use the OPRA results from 2015, then Super Kamiokande from 2018, and IceCube from 2019. And here KM3NeT from this year. And you can see that even with ORCA 6, so only 6 out of 115 detection units and only 433 kiloton years, we managed to have very comparable results, also in terms of error size. So that's pretty nice. And from there, we can think about how we will improve in the near future. So currently, you can see in this plot the date versus the exposure of the detector in megaton years. The ORCA 6 data I've been talking about are about somewhere around here. Since then, we've measured a lot. So now we have 2.79 megaton years of data available. And to get some estimate of how our error on the tau neutrino cross-section will improve, we have this plot here. It's showing the data taking period with the full 115 DU ORCA detector versus the tau normalization. And then you can see the errors decreasing with time. Only using those 2.79 megaton years will bring us somewhere here. So from around 100% error, we could go down to below 20%, just quite the improvement. And at the same time, I've shown you our beautiful tau neutrino sample. We will get better than that. We probably are already. So we will make one of the most impressive tau neutrino samples that the Earth has ever seen. I'm bragging a lot, sorry. Anyways, so to make it a short summary, yeah, so I've shown you our first result for the tau neutrino normalization and, with 433 kiloton years of data. The results have been published. So here's the archive link. If you need something to read in the evening, just click the link. And then as a small disclaimer, well, we have been using for this analysis only 5% of the final detector volume. The next couple analyses will improve the error by a lot, factor 5, for example. So you can imagine that it looks like this in the near future, with even where we will even be able to like manage to get the shape or fit the shape of the normalized fit the shape of the cross section as well. Anyways, that's all I wanted to show. So thanks for listening.
Are there any questions?
This is very cool work. So have you, in KM3NeT, tried to start seeing double banks?
Oh, well, so we don't really approach that in ORCA because double banks usually are only visible at very high energies, right? And ORCA is mostly optimized for the lower energies.
What about double pulses? That's more what I meant. Like when the separation between the first and the second bang is very small, so you just see two BAMs in the same photomultiplier.
I don't think we have looked into it yet.
Okay.
Sorry.
Yeah, that could be a way to identify new tau. Yeah.
That's true.
Yeah, thanks.
Are there any other questions? If not, let's thanks Sharif again.